My name is Preeti Kassereddy, and today's talk is called Reasonable JavaScript. So I know that everyone just ate lunch, and you all probably have the sleepies, but I'm going to try my best to not make you fall asleep. Okay, so who am I? I'm a software engineer and UI designer at a small startup called Sapien.ai. We build bots for big brands, so chatbots and voice bots. I'm very passionate about JavaScript, functional programming, and overall just the future of what AI can do. And I really, really love writing, teaching, and learning and blogging. Some of you may know me through my blogs and Medium posts and so forth. So one thing that kept coming up over and over again when I was learning to code initially, as well as like every day, is people talk about code being easy to reason about. You know, like React makes code easy to reason about, or one-way data flow makes code easy to reason about, or static types make code easy to reason about, or pure functions make code easy to reason about. You know, immutability makes code easy to reason about. And I didn't really know what they meant by that. Did they mean that the code's easier to understand, it's easier to analyze, less buggy? Like, what do they mean when they say code is easy to reason about? So I kind of did a mental exploration, and I'm going to talk about what I came out with in terms of what it means to reason about code. And so the goals for this talk are talk about what makes code easy to reason about, talk about why JavaScript sometimes makes it hard to write code that's easy to reason about, and then talk about the different methodologies and building blocks that we can use to write JavaScript code that's easy to reason about. And if there's anything you walk away with today, you walk away knowing what it means to actually reason about code. And I've already said easy to reason about like a million times, so someone must keep track of how many times I say it, because I'll say it a bajillion times. Okay, so JavaScript is a fantastic language for many reasons, right? It runs everywhere. It's on every browser, every operating system. It's really versatile, too. We can build all types of things. We can build websites. We can build just basic scripts. We can build IoT apps. We can build bots. We can build APIs. We can now even build native mobile apps just using JavaScript. So it's incredibly versatile. It also has this immediate feedback loop. As developers, I think it's really important to see your work as you're building, that immediate dynamic response. And JavaScript is one of the only languages that give you that, and it's really, really helpful, especially for beginners. The community. This is what kept me and will continue to keep me in the JavaScript community. I absolutely love it, and I think every one of you will agree that the JavaScript community is just unique in a lot of different ways, and it's awesome. Overall, it's beginner-friendly, and the reason I say it's beginner-friendly is because unlike most other languages, there's no compilation step, there's no complex developer environments, you can just write code in a text editor. There's no type system. There's global support in any browser, immediate feedback loop, like I said earlier. But all these things that make JavaScript really beginner-friendly is also a blessing and a curse, because the same characteristics that make it easy to learn are also what make it sometimes difficult to write code that's easy to reason about. And I'll just start off with a quick example so you can see what I mean. So I have a function that calculates the area. And all it does is take an array of radii and iterates through the radii and calculates the area and returns an array of areas. Now, as good programmers, let's go ahead and understand our program's behavior, right? First question we might ask is, does it even work? And so we test a bunch of different inputs. We pass in an array of radii, and we test that the output looks reasonable, and it looks pretty reasonable. So I'm going to say that it works. But we also want to ask, does it do anything that we don't want it to do, right? So let's say we do that again. And this time we check what the original radii is, array of radii, and we see that the function mutated that original radii, that original array of radii. So this is already kind of giving a red flag, because what if we needed that array of radii later on in the program, right? We just completely mutated it. Another question we might ask is it consistent in its behavior? So we passed in 1, 2, 3, we get a result, some time passes, and then some evil programmer on your team decides to change your pi variable to 500,000. You run that function again, and you get some ridiculous number. So because the pi was global, it's not predictable in this case. It's not consistent. Does it properly handle all possible inputs, right? So let's say our array of radii was undefined. How does our function handle it? Well, it just throws its hands up and throws an exception because we didn't handle that. So we go back and we're like, okay, let's redesign this program. Step 1, let's not mutate the original argument, and instead let's return a new array with the areas calculated in it. Then we say, let's remove any global dependencies and move that pi inside the scope of the function, and then have the new array and return the new array. And then let's now also handle invalid inputs. So if you might check if the radii is undefined, do some error handling. Right now I'm just doing some basic error handling, but you might also check that it's non-array inputs and do some error handling, and then you finally calculate the result if the input is accurate. So let's go back and understand our improved program's behavior. So does it work? It does work. Does it mutate the original array? It doesn't. Is it consistent in its behavior? It looks like even if we mutate our global pi variable, our function is consistent because we moved another pi, we put pi into the scope of the function. And does it handle invalid inputs? So if you pass an undefined, it throws the error or handles the error however we chose to handle it. And same thing with passing anything else, like an object or non-array inputs. So it's looking good so far. I'm going to do a little bit more battle testing, though. What if we pass an array, but we put an undefined in it? What we end up getting is nan, because in JavaScript, undefined squared is apparently nan. And then if we pass an empty string into the array, in JavaScript, undefined squared is 0, so we get 0. All right, so let's go back and fix our program again. This time, I'm also going to do some error handling, input checking when we're iterating through the array to make sure that the radii, each of the radii in the array are actually numbers. And finally, it works as intended. Okay, so what did we learn? Reliance on global variables causes our programs to be unreliable. This is something everyone probably already knows. Mutable data can lead to unintended side effects. Because we were able to mutate the input array, there's no restriction on it. We did mutate it, and it did cause unintended side effects. Having no way to restrict the type of data that can be passed into a function makes you think really, really hard about error handling. And lastly, type coercion, where you saw string squared becoming 0 and undefined squared becoming nan, that makes it harder to predict the behavior of code. So, and realistically, when we go back to our final program, when you think about this, is this something a beginner would even think of writing? And I'm going to say probably not. So this is why some people get frustrated with JavaScript. There's no compile time restrictions. It allows you to do anything, but you will do anything. So one possible conclusion is just to say that you can't write code that's easy to reason about, and then just give up. But I'm here for the same reason you are. I think we all love JavaScript for whatever reasons that you like it for. And so I'm going to say that My proposed conclusion is with a little bit of extra effort, you can actually write reasonable JavaScript. And so that's what the rest of this talk is going to be about. We're going to explore a few different building blocks that will help us write code that's easy to reason about. But first, let's actually define what makes code easy to reason about, so that when we look at these building blocks, we can see how that building block helps us in writing code that's easy to reason about. I'm going to propose that code is easy to reason about when it doesn't affect or mutate any external state, so there's no side effects. I'm going to say that code is easy to reason about when it doesn't rely on external state. And I'm going to say that code is easy to reason about when it always returns the same corresponding output for a given input. Because what this will lead us, as I'll show you, is programs that are easier to understand the intent of, easier to reuse, easier to maintain, easier to refactor, easier to test, and hence easier to reason about. So let's go ahead and start. First thing, unit tests. This is a very obvious one. I think most of us already do this, but I'm going to talk about it anyway. So we have our program, and we might write a test to make sure that it works and it passes. And as good JavaScript developers, we also write a test to make sure that invalid inputs don't work and that it throws an error. This time, it doesn't pass because our program doesn't throw the error. So then we go back, we fix our program, we make sure that we're checking for the type of the input, and then we run our test again, and it does pass. It does throw. Okay, so going back to the things that define what makes code easy to reason about, how do tests help, right? Does it ensure that code does not affect or mutate external state? Not really. Does it ensure that the code doesn't rely on external state? Not really. Does it ensure that the program always returns the same corresponding output for a given input? I would say yes, it does that. And there's a lot of other reasons to write tests, right? It verifies that your code actually behaves correctly. It tests error cases and edge cases. It serves as living documentation. And you can make changes without fear because you can refactor, and if your tests fail, you know something went wrong. Second building block, types. This is not something we really have in JavaScript, but I'm going to say that it does make code easy to reason about because we do have tools that allow us now to add types to JavaScript. So what is a type? A type is a classification of data which tells the compiler or interpreter how the program intends to use the data. So it basically defines the set of inputs and outputs. So because JavaScript doesn't natively have types, I'm going to use something called Flow. Some of you may have heard of it. Facebook, open source, put it out. It's a static type checker that you can use on JavaScript. There's another alternative. You can also use TypeScript, which I use heavily. I use both Flow and TypeScript, but I chose Flow today just because it was a toss-up, and they're both pretty similar, honestly. So I'm going to go ahead and add types to my program. And if you've never seen types, it'll feel a little bit funky and clunky and weird looking at first, but you'll get used to it pretty quickly. So I'm saying that pi is a type number. Then I'm also saying that our input radii is an array of numbers, and our output radii should also be an array of numbers. Now, the benefit of this is if you run this flow checker and pass in an array, it'll just say found 0 errors. But what also happens is if you pass in invalid inputs, at compile time, it'll throw an error. It'll say, hey, you told me that you're going to put in an array of numbers, but you put in a string in your array, so I'm going to throw an error. And it's giving you this warning while you're coding before you deploy it to your customers so it doesn't throw an error in production. And so there's a lot of other benefits to types. One, it mentally, at least for me, I've noticed, separates your data from your behavior. Because when you're defining your types, you're thinking about your data first, and you're defining the type of that, and then you're thinking about the behavior on that data. And that mental separation is significantly helpful. Second, it serves as documentation. So I pulled this out of a code base that I worked in a few months ago. And basically, it's a function that apparently generates some params. And when I looked at it, I was like, all right, I don't really know how to use this function because I don't know what quote and commit and amount, like I don't know what types they need to be. Is quote a string? Is it a number? Is commit a Boolean or a number? I didn't know what these are. So then I went and dug through the code and wrote some JS doc style documentation so that future users of this function can know exactly what to pass in. This is great and all, but comments quickly go out of date. Documentation goes out of date. I hate writing comments and documentation. I hate updating comments and documentation. I don't do it, so there's like 99% chance this thing will get outdated in like a month. And so, but if you had types, you can typify your input arguments, quotes a Boolean, commits a Boolean, amounts a number, and then anytime you update the code, you have no choice but to update the type. And anyone who looks at it knows exactly what to pass into this function. So code doesn't go out of date. Another benefit is it removes all that convoluted error handling we did. So if you go back to our typified program, we don't have any error handling here because our types are taking care of that. We've already told our type system that we're passing an array of numbers and it should return an array of numbers. So there's our error handling for us. There's lots of other benefits that I can go on forever. I can create a whole presentation on types, but it removes entire categories of bugs, earlier detection of mistakes, as we saw. It gives you this guarantee as a programmer that if it compiles, it runs most of the time. You can refactor with greater confidence, and it serves as a domain modeling tool. I wrote a blog post about this if you're curious about all these other benefits, but I'll leave those out for today. So going back to our mental model of what makes code easy to reason about. So do types ensure that code does not affect or mutate external state? Not really. Do types ensure that code doesn't rely on external state? Not really. Do types ensure that code always returns the same corresponding output for a given input? I want to give that a maybe because it does ensure it gives the same corresponding output type, but it doesn't guarantee the actual value is the same. But we saw that types do offer us a lot. And so I'm going to say types do make code easy to reason about regardless. And I'm going to say the reason it does that is because what types give us is they give us the guarantee that the code works as intended by the programmer. Next building block, immutable data. So what is immutable data? Immutable data is when an object state cannot change after it's created. And if you want to change the state of if you want to change an immutable object, you don't. Instead, you create a new object with the changed value and point your reference to it. So what does this mean? Well, okay, let's take a typical object in JavaScript, and if I wanted to update my age next year, I can do my age equals my age plus 1. This is not immutable because it mutates the age property directly. To show you what I mean by immutable data, I'm going to use a library called Immutable JS. There's other immutable libraries out there. I'm not by no means favoring this, but this was just what I used. And what Immutable JS allows us to do is create immutable data structures in JavaScript. And so I'm going to use the immutable.map function to create the same object, but make it immutable this time. And now, if I want to update my age a year from now, I'll set a new object and point my reference to that new object. And this time my age will be my me_today.getAge+1. This is just how you update maps in Immutable.js. And then what you get is every time you change an age, what Immutable.js does is it'll create a new object. It'll never mutate your original one. And so even if you log your original one, you'll see that it's intact. So if we go back to our area function, instead of passing in an array of radii, we're going to pass in a list of a same array of radii, but this time it'll be an immutable array. So we won't be able to mutate it even if we tried. And because of that, we have to use the map function, which always returns a new array with your mapped values. And so that's what we do. And now, if we actually check the equality of the original array of radii versus the output, we see that it didn't get mutated. You're like, so what? Why do I give a shit? Okay, so I'm going to show you this example, and I hope I somewhat convince you of why sometimes immutable data really helps us. Who's gotten this in an interview question? Yeah, and basically, this is an in-place quicksort function. You are iterating through the input array, and for all the items lower than you pick a pivot, all the items lower than the pivot, you move it, and then you put your pivot in the right place, and you run your quicksort recursively on either side of the array. This is great and all, but I feel like this every time I write that function, like I have no idea what I'm doing, and I get so scared that I miss some variable or some of one of the J's or I's is in the wrong place. And so let's say I did make a mistake, right? Instead of putting the J++ right in the top of the if block, I put it at the bottom. This is so easy to happen in an interview. And then when I actually run this function, what I get is 134, 34, 34, 34. And so I don't get the job. Now, what if I said that if with using immutable data, the function can look like this? Because I can't mutate any of the arrays, I'm not going to do an in-place. I'm not going to do anything in place. I don't need to keep track of J's and I's and K's. Instead, I create a new list every time. And what I do is first I set the pivot value, and then I set the remaining of the array, and then I find all the values less than the pivot. This is every time a new array, and all the values greater than the pivot, new array, and I simply concat the pivot with all the items less than the array, all the items greater than the array recursively. So now it actually works, and I get the job. And the reason it looks so simple is because we don't have to worry about intermediate variables and state and keeping that all in our mind. Every time, you're really just creating these expressions and not having to worry about, again, like the I's and the J's and the K's. Now you look like a baller, and so you get a job. Okay, and some people might be thinking, well, if you're creating that many new arrays, what if your list is really long and you have performance problems? And one of my favorite quotes by Wes Dyer is, make it correct, make it clear, make it concise, make it fast, in that order. So if you really have performance requirements, then think about maybe not using immutable data. But I would say if it makes it clear and concise, I'm all for it. So overall, why immutable data? Well, when data doesn't change, we can just use the data and not think about whether making changes to it is safe. No one can mess with your data, nor you theirs. And so going back to our Melton model of what makes code easy to reason about, does immutable data ensure that it doesn't affect or mutate external state? Yes. Does it ensure that it doesn't rely on external state? Not really. Does it ensure that it always returns the same corresponding output for a given input? Usually, yes. Oh, no. Sorry, I was thinking something else. Does it guarantee that the code works as intended by the program? This is what I meant. It does, because you know that the data is immutable, so you know that every time the function should return the same output for the same given data. Okay, next building block, pure functions. What is a pure function? Well, let's start with what is not a pure function. When something relies on external state, it's not a pure function. So then the obvious next definition is a pure function is something that relies only on what's explicitly passed to it as arguments, and it doesn't have any side effects. Example. If we have an increment function that takes nothing and increments our global count variable, this is not immutable. This is not pure, because it's relying on the global count variable. And we've mutated the count variable. On the other hand, if we have a similar function, but this time it takes the count as an input and uses that, then it's not relying on anything global. And so this time it is pure. Another example. You have a function that simply determines whether some amount exceeds the user's buy limit. And to get the limit, you have to go fetch it from the API. This is not pure because it's relying on some external state. It's making an API call. One of the reasons impure functions are hard to work with is because testing an impure function is just a lot more work. When something relies on something external, what you have to do is set up mocks, and then clean up your mocks and your tests. And I know a lot of you probably don't like mocking, and so your tests look like these long, complicated things. Whereas if you purify it, meaning you assume that the function knows what the limit is in advance and you pass it in, then this kind of function becomes so much easier to test because you're not having to mock everything. So going back to our definition, does a pure function ensure that code doesn't affect or mutate external state? Does a pure function rely on external state? No. Does a pure function always return the same corresponding output for a given input? Yes, because it doesn't rely on external state, it always returns the same output. And is it guaranteed to work as intended by the program? Again, yes, because it's not relying on anything external. It usually works as intended. And then when you combine pure functions and immutability, like you're unable to mutate external state, then what you get is referential transparency. And what this means is you have the ability to freely replace an expression with its value and not change the behavior of a program. So why do we care about referential transparency? Because now, finally, when we combine pure functions and immutability, what we get is code that doesn't affect or mutate external state because it can't. It doesn't rely on external state. It always returns the same corresponding input for a given output, and it's guaranteed to work as intended by a programmer. So it checks all the boxes. And the last building block I want to talk about is taking advantage of functions as first-class entities. And I'm going to give you 4 examples, and there's a lot more ways you can use functions as first-class entities, but I'll give you 4. But let's first define what it means for a function to be a first-class entity. It means you can refer to them from constants and variables. It means you can pass them as parameters to other functions. It means you can return them as results from other functions. And I think that's it. So why use functions as first-class entities? That's exactly what I'll show you. One way to use functions as first-class entities is replace loops with higher-order functions. Higher-order functions are functions that work on other functions, so they can take in functions as arguments and return functions as the return value. So an example is we have our original calculate area function. Map, I'm using a library called Ramda. You can use any utility library, but the map function is a higher order function where you pass in your mapping function and your array, and it returns a new array. And when you use a higher order function, you don't have to worry about the looping because it abstracts it away from you. Similarly, if we had another function, like sum of odd squares, where you had to find the sum of all odd squares less than 1,000, this is what it would look if you didn't use higher order functions. You have to create while loops and for loops, iterate through your array, square the values, find all the ones less than 1,000, and then sum them up. But if you were to use higher order functions, what you can start to do is just use the basic higher order functions like map and filter and sum, which are things that Lambda offers you. And you create simple functions like give me the value, or you create simple functions like less than 1,000 that determine if a value is less than 1,000, or determine if a value is odd or square. And then you simply just pipe, you take your array and you first map you square over the values, you take the ones that are less than 1,000, you filter for the odds, and then you sum them, and you have your value. So how do higher order functions help? Well, one, do they ensure that code doesn't affect or mutate external state? Not really, but I'm going to give it a maybe because a lot of the higher order functions like map and filter do return new arrays, and they don't really mutate the original array. Does it ensure that the code doesn't rely on external state? Not really. Does it ensure that code always returns the same corresponding output for a given input? Not really. And does it guarantee that the code works as intended by the program? Not entirely. But why higher order functions? Because as you saw, the code becomes shorter and less clunky. It becomes easier to read, more descriptive, and in essence, it allows us to define computations by defining what we want instead of how we want, because the looping is abstracted away by the higher order function. Overall, it's just more information and less noise. Another suggestion I have is to parameterize everything. So let's go back to our calculate area function. And later on, we're told that we need to also have a function that calculates the diameters of these radii. They look very similar, so we decide to abstract the common code and create a simple action function out of it. So one calculates the area, it takes a radii, calculates the area, one takes a radii and calculates the diameter. And we create a generic action function that takes our action and some list and maps over that list and performs the action on it. We parameterize our behavior. And so we can get our areas and our diameters. Then you can start to create generic functions everywhere. You can also square values, double values, negate values, and pass any list. And you can use a generic action on list function and pass any of your action functions in and a list and get your responses. So does parameterizing ensure that code doesn't affect or mutate external state? Not really. Does it ensure that code doesn't rely on external state? Not really. Does it ensure that code always returns the same corresponding output? Nope. Does it ensure that it guarantees to work as intended? Not really. But it does allow us to create this very generic function where you can pass any list and any data. And so that function becomes much more reusable. Secondly, it also decouples the behavior from the data. Third suggestion, almost there, partial application. So this is another way to use functions as first-class citizens. Partial application means we can turn a function that expects multiple parameters into one that will keep returning a new function until it receives all its arguments. That's a whole lot of mouthful, so let's see what it means. Example, so here's a typical JavaScript function. It takes a fee and some amount, and it applies the fee to that amount. Every time we want to use it, we pass some fee, and we pass the amount, and we get the result. But if we passed in just the fee, it throws a big fat nan. If we were to partially apply, we can start to create specialized functions out of our generic apply fee function and do apply bank fee and just pass in the fee. Don't worry about passing the actual amount. You can pass in the data last. You can say another function for apply credit card fees and another function for applying PayPal fees. And you're partially applying that fee, but passing in the amount later on when you need to use it. Now we can pass in the amount at any time and just use these functions. So that's partial application. And you're probably like, so what? Well, I think I'll try to convince you on one common use case. And the benefit of this comes because with partial applications, we can pass the data last. And so you might have seen code like this where you have you're fetching data from an API, then you're parsing through the data and getting your result and formatting your results. To zoom in a little bit, let's say this function fetches some payment methods, then it grabs the data off the data property from the response. Then for each of the payment methods, it checks if the allow by property is true. If it is, it pushes it to a new array, returns that. Then it checks if the limit is greater than 0 and returns that. And finally, it iterates through that result array, formats it to just get the ID and the name off each of the items in the array, and returns the formatted payment methods. Now going back to what we just talked about, which is higher order functions, we can already clean this up by using higher order functions. We can replace all those loops that we had and all the data wrangling and just use 2 filters and a map to get our result. And already this looks much better. But what if I can propose to you that with partial application or currying, it can look like this? Because our data can come last, all we have to do is worry about passing functions to tell it what we want. So first we want the data property off the response. Then we want to filter for all the items where the allow by property is true. Then you want to filter for all the ones where the limit.by, that remaining path, is greater than 0. And then finally, you want to pick just the ID and name off of it. And each time, the data comes from the previous function. So it goes from one then to the next then to the next then. But you just pass the data last, and you worry about what the actual functionality is first. So what are the benefits of this? Well, does it ensure that it doesn't affect or mutate external state? Not really. Does it ensure that it doesn't rely on external state? Not really. Does it always return the same corresponding output? Not really, but kind of. Does it guarantee to work as intended by the program? Not really. But it does give us a huge benefit in terms of readability. It's a powerful way of transforming your data. You can use functions as generic building blocks. And it allows us to do dependency injection, like with the fee example. Okay, I'm running close on time, so I'm going to rush through composition, but some of you may have known already what this is. So composition is the 4th example I'll give you for how to make code that's easy to reason about. And composition is once we get to the idea of passing functions as parameters to different functions, we can start to define ways to combine functions together. And so a quick example is I have a function that calculates the tax and shipping and handling. And it takes an amount and just calculates shipping and times it by a tax amount and adds $10 shipping and handling. Ooh, sorry. Yeah. And if I were to use composition, I can simply separate the apply tax functionality, separate the apply shipping and handle functionality, and compose them together, meaning first it'll go through apply tax, and then the apply shipping and handling function, and then that's my total cost. So composition is when you run your data through several functions in a row. So then later, let's say you need to add a gratefulness surcharge or something. So you can either update your function to just add the $4 gratefulness surcharge, or you can use composition and create a new simple function that adds 4 as a gratefulness surcharge, and you can pop it onto your compose stack, And now it first applies tax, then applies shipping and handling, and then applies gratefulness surcharge. And later, if you're like, okay, I don't want to apply this surcharge anymore, I can also just compose it with the other two. And later, you want to add a 5% discount. You can go and update your function to add the 5% discount and do this. Or you can use composition and create a new function called apply discount and simply compose and put the apply discount as your in your composition stack. And then let's say we want to format money later. I'm not even going to try to update the original function, but I'll show you how you can compose. You can create a new format money function and just pop that on top of the stack. So why composition? Because each function is useful on its own. You can easily create fresh new functionality from existing functions. We saw how we can remove the gratefulness surcharge or keep the gratefulness surcharge without updating our code. You can break apart pieces of behavior and test them independently. Overall, it declutters code and adds readability. But if you go through our checklist, we'll see that it doesn't really meet any of the requirements. But we saw how taking advantage of functions as first-class citizens, whether you're using higher-order functions or pure composition or partial application, you saw that it encourages to use functions as a primary unit of abstraction. And so what happens is we ended up creating small, independent, composable functions to model and solve any problem. And it seemed like there were a lot of benefits, as we saw, so I'm going to propose that when you use functions as first-class citizens, you get something called modular and generic code. And this is also what makes code easy to reason about, because what modular and generic code gives you is code that's easier to understand intent of, easier to reuse, easier to maintain, easier to refactor, and easier to test. Overall, easier to reason about. So recap, tests, types, immutable data, pure functions, functions as first-class entities, which were these four. And I'm going to do a grand slam of putting it all together. It's a little much. We, of course, don't have to do this in JavaScript, and I'm not by any means proposing that we should do it, but I just want to show you what's possible. So I'm going to use map and pipe from Lambda and Immutable.js. I'm going to add types to our py. I'm going to create a generic type function, and it's a type of it's an action function that takes a value and returns the number. Then I'll create a calculate area function that's of type action, takes a radius and calculates the area. Then I'm going to create a generic do stuff on list that takes any list and any action and returns a new list. And it maps over that list and performs the action on it. So then if you want to use it, I have an original radii, and that original radii will be immutable. I can do stuff on the list, and I don't mutate the original array. And later on, I can also format my areas nicely by truncating it. And then I can use composition to pipe it through first to calculate area, and then to format it nicely, and then I get a nicely formatted radii. You gotta give me props for that. Okay, overall, I'm not proposing again at all that we should use all of them, but I think it's important to realize that you can pick and choose which ones you think will make your code easier to reason about. You saw some of the benefits. I went through it a little bit fast, but these are just building blocks that we have available to us. So overall, JavaScript strives to be an incredibly dynamic and flexible language. This sometimes puts the burden on the programmer to consciously write good code, and makes it easy for someone to bash on JavaScript for its dynamic typing, aggressive type coercion, mutable data structures, whatever. You've seen the JavaScript haters. But just remember that JavaScript wouldn't be where it is today if it weren't this way. Its incredible flexibility and forgiving nature is exactly what gets beginners in the door, and it enables it to be used for a lot of different things. And so we're fortunate enough that there are tools and methodologies that I showed you in this presentation that enable us to write good JavaScript. And so I call this a win-win situation. So let's go write some code that's easy to reason about. That's it.